Okay, good morning, students. So this one is for geometry, semester 2, and unit 5, the pretest analysis. So we'll take a look at that, some of the problem here. So what's the number of possible outcome when tossing 4 coins at once? So anytime that we toss a coin, so we do have two possible outcome there. So either the head or the tail. So the way to do it, so 4 coins. So the way to do it is by taking that 2 to the power of 4. So 2 to the power of 4, which is 2 times 2 times 2 times 2, multiplied by 2 for consecutive time. So you'll get 16. So the way that you set it up, so the number of chances, the possible outcome we have is 2. So the head or the tail is 2. And then 4 coins to the 4 power. So you can put it this way, 2 times 2 times 2 times 2 times 2, because that's 4 coins. 1, 2, 3, 4. So multiply them all together, so then that would be 16. And now the next one is quite similar, so 5 coins, so 2 to the 5th power, so 32. And then 6 coins, 2 to the power of 6, 64. And then question number 2, so which of the following is the elements in the sample space for first rowing a number cube and then tossing a coin? So if that's a cube, we do have how many faces that we have for the cube? So it's 6 faces. So the number of chances of getting a number, so then that'll be 1 out of 6. And then tossing a coin, so it's 1/2. So the things that we need to find out the sample space. So the first one, it's always coming out with the number. And then the second one, then it's always either the head or the tail. So the one that's correct, which is answer B right here. So it's always the number first, and then the second one, the second sample space would be either the head or the tail. The rest of those are wrong. This one is just number, head, tail, and then this one is just swap the outcome, the sample space outcome. So it's head and 7. And then 2B, again, so we want to toss a coin first, so the number is going to be the first outcome. And then the other one is throwing a number cube. The first one is actually the head or the tail. So it's either, okay, so it's either B or D. But tossing a coin and rowing a number cube. The number cube, there's no 8 because that's only 6 faces. So it's 1, 2, 3, 4, 5, 6. So cannot be 8. So the only one that's correct, so it's D. And then 2C is quite similar, so let's move on to the next one. So which of the following shows the elements of a sample space for first tossing a coin and then rowing a number cube? So number comes, the coin, so the head or the tail comes out first, and then the number. So the answer is D. So it's all quite similar. Okay, so now question number 4. A large bag of marble contains equal amounts of red, orange, yellow, blue, and green marbles. And Quinn randomly select one marble from the bag. So what's the probability of selecting a red or blue marble? So the way to do it, so this one basically, so let's say that we have one red marble, orange, one orange, one yellow, one blue, and one green marble. So the way to select the first outcome would be consider 1/6. Okay, so and the keyword here it's or. Okay, so we got 1, 2, 3, 4, 5. Well, actually, we do have 1, 2, 3, 4. So we do have 5 different color of marble. So selecting the first one would be considered 1/5. And then the second one that we select would be another 1/5. So 1/5 plus 1/5, then that would be considered 2/5. And then 2/5, 2 divided by 5, then that would be 0.4. So the way that you want to do it, so it's like this. So the first probability, so let's say selecting the green, because that we do have 5 different colors, so selecting the red, it's considered 1 out of 5, and then selecting the other color, so it's 1 out of 5 again, but instead of multiplying it, because the keyword is or, so that means we're doing addition, so it's 2/5, and which is considered 0.4. Okay, so now let's see what else that we have for the rest of this. So this one, selecting a red, blue, or yellow marble. So if that's the keyword or, okay, so similar to the first one, so it's 1/5 plus 1/5 plus 1/5. But I try to do it that way. Let's see, a red, blue, or yellow marble. Okay, so the chances of selecting a red blue, so the probability for that one would be considered 2 out of 5. So 2 out of 5 plus 1 over 5, then that would be considered 3 over 5. And then 3 over 5, 3 divided by 5, then that would be 0.6. The reason why the first one is 2 out of 5, because that is saying that selecting a red, blue, and then after that is the keyword or yellow marble. So selecting red, blue, so the probability for that would be 2 out of 5. And then, or yellow marble, so the probability for that would be 1/5. So 2/5 plus 1/5, 3/5. So it's 0.6. So got to be careful with the wording here. So probability of selecting a red, blue, yellow, or green marble. So the probability of selecting a red, blue, yellow marble, then that'll be considered 3 over 5. And then, or green marble, then that'll be 1/5. So 3/5 plus 1/5, then that'll be 4/5. 4 divided by 5, then that'll be 0.8. The Venn diagram. So the Venn diagram is something that, they share in common with those two sets. So let's say we do have two events, event A, event B. And also there's an overlapping region here. So this one we want to find out, things that they share in common. So anytime they see that probability of event A union with event B. So that means you want to combine those two probabilities together. So we got 0.4 plus 0.45, then that'll be 0.85. But don't forget, we need to exclude out the one they share in common because we don't want to count those probability twice. So 0.85 minus 0.1, then that'll be 0.75. So the way to do it, so let me just open up the new slide here. So anytime they see that it's an overlapping event, so let's say that the probability of event A union with event B. So it's about probability of event A plus probability of event B, and then minus the one that is shared in common, event A intersects event B. So see the union, so the parabola like this, that means union, or the U symbol. And then you see the upside down U, that means intersections, or intersect. So that's why we started with adding those two events probability first. So we started off with 0.4 plus 0.45. So plug in that, the probability, 0.4 plus 0.45. And then once we combine them, and then we subtract 0.1. So we got 0.85 minus 0.10, then that will get 0.75. Okay. And then the next one is quite similar. So this one, finding that the probability. So 0.3 plus 0.35, then that would be considered 0.65 minus 0.1, then that would be 0.55. And the other one is also quite similar. So finding the probability of event A union event B. So anytime that you see the Venn diagram, if that's asking about the union, always, so we want to subtract the one that they share in common. And now the next ones. So Miss Jackson is choosing one of 4 students, Adam, Bob, Claudia, or Donna, to read an essay to the whole class. So what's the fair way to do this? So the way to do this is to select people. So have the student put their name in the back and then shade the back and choose a name without looking it. So this one, that's guaranteed, we just want to select the student randomly without looking at the name. So Coach Martinez is picking one of 3 students, Bella, Chrissy, or Destiny, to be team captain. So what's the fair way to do this? So the way to do it, row a number cube. If 1 or 6 comes up, pick Bella. If 2 or 5 comes up, pick Chrissy. If another number comes up, pick Destiny. So each person have 2 numbers representing, the chances of being picked. And now, and for 6C is quite similar. So Ted is picking one of his 3 children, Ed, Jad, or Nat, to do the dishes. So what's the fair way to do this? So make a spinner with 3 equal size sections. Assign each child 1 section and spin the spinner. The child whose section comes up does the dishes. So fair chance. So which of the following is an examples of independent event? Independent event, that means it just like relying on itself. It doesn't depend on the other kind of event. So getting tails on a coin toss and drawing a king from a standard deck of a card. So tossing a coin and then drawing a card from a standard deck of a cards. So this one, those two events, so they're considered independent because they has nothing to do with each other. They're not affecting the results of one to another. So here's another one, independent events. So rolling a 6 on a number cube and then spinning a 7 on a spinner. Again, spinning the spinner and then rolling a dice or cube. So those two events has nothing to do with each other. Okay, so the rest of this, they're quite similar. So which of the following is an examples of dependent event? Dependent, that means one event happens, it's relying on the other event. So drawing a jack from a standard deck of a card and then drawing a 6 without replacing the jack. So anytime that you want to draw the card from a standard deck of a card, so the first card that you pick, you don't want to put it back to the standard, to the stacks. So that's why you want to choose another one. So that means the chances is getting smaller. The chances is actually getting higher. So that's why, this one, it's one event. The second event, it depends on the first event. So here's another one, rolling a 6 on the first of two numbered cube and then getting a total of 12 on the two rows, okay? So one thing, the second event, it's depending on the first event. And then selecting a red marble from a bag of 4 different color marble and then selecting a blue marble without putting the first marble back. Again, so this one is the second event. So the outcome is relying on the first event. And then question number 9. So there's a 90% chance that a person eat dinner, a 60% chance a person eats dessert, and a 50% chance the person will eat dinner and dessert. Which of the following is true? So eating dinner, eating desserts are dependent events because that probability of people eating dinner times probability of people eating dessert is 0.9 times 0.6, which is 0.54, and which is not equal to people eating dinner and dessert. So the probability for that one is 0.5 only. So once you come up with the exact same events, once you come up with the exact same probability, so that means those two events, the event would be considered independent. But once you come up with different probability there, so that would be considered dependent. Again, if that P of dinner times P of dessert is the same as the probability of P of dinner and dessert. So if that's the same probability, that means it's independent. If that's, well, those two probability, if they're different, that means that would be considered dependent. Okay, so now let's see what else. So this one is quite similar. So there's 80% chance that a person eat dinner, 70% chance a person eat dessert, so similar problem. Again, so you want to multiply those two probability, 0.8, 0.7, so we got 0.56. So this one, once again, is considered dependent. So for those two probability, they're not exactly the same. So 9C is quite similar, so let's skip that one. So number 10. A large bag of marble contains equal amounts of each of 5 colors, red, orange, yellow, green, and blue. In Keisha, select one marble, look at it, and put it back. And then select another one. So find the probability of Keisha, first picking a yellow marble and then an orange marble. So the way to do it, so this one is considered placement. So once you select one marble and then you put it back to the rest of the selections. So what we got here, it's 1/5. Okay, so for the first one. And then after that, okay, but put it back and then select another. So the other one would be considered 1/4. So 1/5 times 1/4, then that'll be 1/20. So 1/20, once you convert that to a decimal, so then that'll be considered 0.04. But let me check one thing real quick. Yeah, I think there's a little typo here, so this one is putting it back there. So 1/5 times 1/4. So that only gives you 0.05, so we don't do it this way. But 1/5 times 1/5. Then that'll be 0.04. So there's no typo here, so putting back, so that means the probability of selecting the orange marble would be considered 1/5 as well, because you want to put in the marble back to the selection. So it's 1/5 times 1/5, so it's 1 over 25, which is 0.04. So here's another one, so putting the marble back to the selection, so 1/5 times 1/5, 0.04. And then 10 colors, so 110 times 110, then you got 1 over 100, 1 over 100, then that'll be 0.01. So number 11, a coin is tossed 4 times, so which of the following represents the probability of a coin landing on hat 4 consecutive times? So the way to do it, so in order to get a hat, so the chance is considered 1/2. Okay, so let me just do it right here. So 1/2. So since you want to do it 4 times, so it's 1/2 to the 4th power, so it's 1/2 times 1/2 times 1/2 times 1/2, which is 1 over 16. And a coin tossed 7 times, so which of the following represents the probability of coin landing on tail all 7 times? So this one is just 1 over 7 to the 7th, 1 over 2 to the power of 7. So 1 over 2 to the power of 7, then that'll be 1 over 128. So it's quite similar to 11a. So 1/2 to the power of 8, so it's 1 over 256. And now question number 12. So some red, white, and blue candies were placed in a bowl. Some contains nuts and some do not. Suppose one of the candies were chosen randomly from all the candies in the bowl. So which of the following represents the conditional probability? So conditional probability is showing that the probability that it does not contain any nuts, and given that the candy is blue. Okay, and here's another one. It's quite similar. So the probability that does not contain any nuts, and given that the candy is red. So conditional probability. So the probability that the student is left-handed, given that the student is a boy. So 13, so which of the following is an examples of conditional probability? The probability that a person will order pie, given that she asked to see a dessert menu, excuse me. So anytime that I see the conditional probability, so that means one event, so it happens on top of the other events, okay? So this one is all about the examples for the conditional probability. So the probability a person will ace a test, given that a person got a good night's sleep the previous night. So again, one thing happens and then that affects the other event. So suppose A and B are dependent events. So if probability of A equals 0.4, probability of B on top of A equals 0.8. So that means the probability of B over A, that means it's depending on event A. So what's the probability of event A intersects with event B? So the way to do it, so it's basically just need to multiply those two numbers. Because that probability of B, it's relying on event A. So in order to find out what they intersect here, so it's just 0.4 times 0.8. So 0.4 times 0.8, then you get 0.32. Again, if one event relying on the other event. So in order to find out where they intersect, things that they share in common for the Venn diagram, so you just need to multiply those two probability. So 0.3 times 0.9, then that'll be 0.27. So this one's quite similar. Event B depends on event A here. So finding things that they share in common, so 0.5 times 0.6. So 0.30 or 0.3. So now number 15, so you're trying out for school play. The probability that you're chosen to be in the play is 0.4. And the probability that you get a lead row is 0.1. So what's the probability that you get a lead row given that you're chosen to be in the play? So the way to do it, so basically we just need to combine them together. So one thing, so looks like this two probability, they have nothing in common. So 0.4 plus 0.1, then that'll be considered 0.5. But you try to think about that way, so which is not correct. And again, so read through the last the statement here. So what is the probability that you get a lead row? Okay. And given that you're chosen to be in the play. So the way to do it, so what happened, we try to multiply it. So once you multiplied it, so one thing is relying on the other, so 0.4 times 0.1, again, so just finding things that they share in common, then that would be 0.25, 0.0, well, let's see. If you just multiplied it, then that's also incorrect. Then that would be considered 0.04. Oh, you know what? One event is relying on the other, so this one should be considered 0.1 because that is the probability that you get a lead row first. So it's relying on the probability you're being selected to be in the play. So 0.1 over 0.4, then that would be considered 1 over 4, which is 0.25. So again, one event is depending on the other event, on top of the other event. So you're trying out for school play, the probability that you're chosen to be in the play is 0.5. The probability that you get a lead row is 0.1. So what's the probability that you get a lead row? And given that you're chosen to be in the play. So 0.1 over 0.5, which is what? 1 over 5, which is what? 0.2. So 0.1 divided by 0.5. So 15C is quite similar, so we can skip that one. So again, dependent, independent events. So probability of A is 0.25, probability of B is 0.3. And they're both considered independent events. So that means probability of A or B, then that'd be 0.25. So what's the probability of A relying on B? Well, this one has nothing to do with probability of B. So it's only what? 0.25. Because both of those two events, they're considered independent. And then this one is quite similar, independent events. So one event has nothing to do with the other. So this one is asking what the probability of B over A is. So probability of B, then that would be what? 0.5. And probability of A over B, then again, independent events. So probability of A, 0.2. So now, what happened once you deal with the table? So this one is like a conditional probability again. So the chef at the school cafeteria asked 100 male and 100 female students whether they like peas. 58 of males said they like peas. And then 64 females said they dislike peas. So which two-way table correctly showed this result? So 100 male, 100 females. So 100 male, 100 female. And then 58 of males said that they like. And 64 females said they dislike. So for the like and dislike, you want to put in two columns. So 58, so for the one that who likes the peas, so 58 males, 36 females, so the total would be 94. The one that's disliked for the males, 42, and then for the females, 64. So the total would be 106. Again, it would just match up the column, so 100 males, 100 female, so 58 plus 42, that's 100. And then 36 plus 64, that one is also 100. So combine all those people together, then that'd be 200. So same thing happened with that 94 plus 106 is also 100. So it's called a two-ways table. And the other one is quite similar, so you just need to set up two columns, like, dislike, and then total. So the row here, set up male, female, and then the total. So the correct solution here, then that would be B. So 17, once again, similar structure. So for C. So now let's find out about the probability of the two-way table. So the table shows that the results of a student survey done by a chef at school cafeteria, what's the probability that one of the student is male and dislike peas? So male, so we do have 58, we do have 100 male, but 58 of those males, they like peas. So what's the probability for that? So a lot of people probably come up with 58 over 100. So that would be considered incorrect. 42, that would be dislike. No, that's also considered incorrect. 29, well, that's something else. The way that to come up with 21%. So here's what you need to think about. So started with the number of male. So the number of male, then that'll be considered 100 over 200. Okay, so you started with the fraction first. So 100 over 200. So selecting the male. And the number of people who like Pete's is what? 58. So 58 over the number of people who likes Pete's is 122. So the way to set it up, then that'll be considered 100 over 200. Okay, so let me just set it up here. So selecting the number of male first, times, and the number of male who likes Pete's. Okay, so let's see, back to the table. So then that'll be 58 over 100. And now from here, you want to just cross cancel. And then for this one right here, you want to reduce. So once you reduce it, so this one divided by 2 first, so it's 100. Divided by 2, then you'll get what? 29. So it looks like it's 0.29 or 29%. But according to what we got here, it's 21. So again, 29% is also incorrect if you try to do it that way. So again, you need to read through the question here carefully. So what's the probability that one of this student is male? So selected the male first. So 58 over 100 over 200. So selecting the male, that's right. And then dislike Pete's. Okay, dislike, not liked, okay? Then dislike would be considered 42 over 100. Okay, so the way that I put in the property, that's incorrect. So for this fraction here, so let me just start it over. So selecting the number of males, so 100 over 200, because that's 200 people. The other 100 is female, so only 100 of those are male. And then times 42 over 100. Again, cross cancel. So once you cross cancel, this one here divided by 2, so that's how we got 21%. Or 0.21. Okay, so let's go back here. So the one that I select is the one that like Pete's, okay? But actually supposed to be the one dislike. And here's another one, so same kind of problem. So what's the probability of one of the students is female? So female this time, 100 over 200. So this time, like Pete's. So like Pete's, then that'll be 64 over 100. Okay, so the way to do it, so then that'll be 100 over 200, selecting female. And then the one that likes Pete's, so let's see, how many people there? 64 out of 100. Again, once you reduce it, you can always reduce it 1/2. So half of 64%, which is what? 32%. You can do it that way too. Okay, so the next one is quite similar, so we can skip that one. So now let's move on to question 19. So a survey asks people of different age whether they get their news by reading the paper. So what's the probability that a person surveyed is under 40 and gets the news by reading the paper? Okay, so two things. So it's under 40. So people who are under 40, so that would be considered 40 out of 80. And then gets the news by reading the newspaper. Reading the newspaper, then that would be 4 over 40. Okay, so let's see. So this one would be considered 5%. If we try to do it that way, so let's see. 1/2 times, yep, 10%, that'd be 5%. So this one is quite similar to number 18. So the first thing that you want to do, you want to find out the people that it's under 40. So under the 40 group, so we do have 40 out of 80. Okay, let's put it right here. So started with that under the group, under 40 years old. So it's 40 over 80. So basically that's just half of the group, half of all the people here. And then the number of people reading the newspaper, then that'll be considered 4 over 40. So times 4 over 40. Again, cross cancel. So this one got 1, 1. 4 goes into 80, 20 times. So it's 1 over 20. Convert that to percentage. Wait a minute. If that's 1 over 20, convert that to percentage. That's right. Would that be considered 5%? Because you multiply by 5, top and the bottom. So it's 5%. So in order to go from 100, in order to go from 20 to 100, so you multiply by 5, top and the bottom. So eventually it's 5%. Okay, so again, quite similar to what we were doing for number 19A and 18A, B, and C. So this one you can skip through all of them. And now what about question number 20? Again, it's two-ways table. A survey asks people of different age whether they get their news by reading the paper. Okay, quite similar to 19. But what's the probability that a person surveyed is under 40? And given that, okay, so this one is a main statement. So given that he or she gets the news by reading the paper. If necessary, round the answer. So this one is not going to be the same way like what we're doing because this one is given with the condition. So given that he or she gets the news by reading the paper. So let's find out the people under 40. So under 40, we do have 40 over 80. And this one is saying that given that he or she gets the news by reading the paper. So reading the paper, then that'd be 4. If necessary, so round the answer. So for the second fraction here, so the first fraction, we're still selecting that people under 40. So then that'd be 40 over 80. Okay, so let me just put it right here. But this one is considered conditional probability. So the second event is saying that something is given here. So given that he or she gets the news by reading the paper. So anytime they see the given condition like this, so whatever that people reading the paper, it's not just 4 over 40. It's actually 4 over 28. Because by the time they're reading the paper, it's not just the one under 40, but also we do have people 40 or years older. They're also reading the paper. So the probability for people reading the paper, so it's not just counting for the group that is under 40, but also we need to include a one that is 40 or older. So it's 4 over 28. So for that probability, then that'll be 4 over 28. And then the rest of this, you just want to cross cancel and then multiply them straight across. So 40 over 80, then that'll be 1/2. And then 2 goes into 4 twice. So now we end up with 2 over 28. And also this one is reducible. So reduce it, so it's 1 over 14. Would that be 14%? So not quite. Okay, let's see what I did wrong here. But according to the final outcome, it's actually 14%. The way that I end up here, it's actually 1 over 14. It's not the same as 14%. Okay, let me go back to this one real quick. So eventually, in order to get that 14%, let's see what we did wrong. Okay, so the probability the person surveyed is under 40. Okay, so under 40, so 40 over 80. And given that he or she gets the news by reading the paper. Okay, let me think about this one. Yeah, this one is one of the interesting ones. So it's unlike the previous one, it's like 40 over 80 and then times 4 over 40. If we try to do it the other way around, okay, so let's say that we try to do it the other way around. So we got 40 over 80 times 4 over 40. Then this one would be considered 1 over 20. The 1 over 20, that would give you what? 5%. which is not correct. But the answer is 14%. Okay, let me go through one of the detailed information here real quick. Okay, so 4 over 28. Wait a minute. Given that by reading newspaper. Okay, what happens if I try to do it this way? So 28 over 80 times 40 over 80. So if I try to do it this way, would that be considered 14%? Okay, so let me just put it into the calculator and see what happens. So cross cancel out first. So this one is 1, this one is 2, and this one turns out to be 14. But that would be considered 14 over 80. Okay, let me check one thing real quick. Yeah, the two-way table sometimes is kind of confusing. Okay, so let's see. 28, people reading papers. 28 over 80, and then times. So the number of people under 40, then that'll be 40 over 80. Yeah, that will give you 14%. Okay, what about if I try to do it this way? Yeah, this one definitely is one of the harder ones. Okay, so what happens if I just put in 40 over 80, because selecting the people under 40, and then the one only reading the paper, and it's under that column there. So 4 over 28, let's see. Oh, you know what? The thing is that there's no need to multiply by anything here. So this one is actually, excuse me. So this one actually is not that bad. It's just like 4 over 28. Okay, so if just think about this way. So people under 40, so we do have the first column, the second column, but we need to select the one that's reading the paper. And this one is showing that it's on top of the event of that he or she gets the news by reading the paper. So the number of people reading the paper is 28. So this one would be the total possible outcome. So the one that reading the paper and it's under 40, so the overlapping column and row would be considered 4. So 4 over 28, then that would be considered 0.1428. Convert that to percentage, then that would be 14%. So this one is just like 4 over 28, so 14%. So now let's try another one here. So survey, it's, okay, people that's what, 40 or above. Okay, so 40 or above, right here in this row, 40 or older. And given that he or she gets the news by reading the paper. Again, the number of people reading the paper, then totally is what, 28? So 40 or older and reading the paper over 28. So 24 over 28. So let's see what that is. 86%, and that's what I got. So again, anytime they see the keyword given, so given condition, so that means it's the total outcome here. So anytime they see that the total outcome, so we just want to divide that number. So find out the one they share in common, row and column, and pick that number, and then divide by the total outcome. So 24 over 28, 86%. So let's try another one here. So this one, a person survey gets the news by reading the paper, given that he or she is under 40. So this time, so we switch the situation. So the probability that a person survey gets the news by reading the paper. So reading the paper, okay, so that would be this column. Like given that he or she is under 40. So given condition would be the total outcome. Under 40, then that'll be 40. Okay, so reading the paper. So this time would be considered 28 over 40. Wait a minute, let's see. Okay, so guess the news by reading the paper. So 28 people reading the paper, but this one is under the 40 years old group. Oh, you know what? It's just 4 over 40. Because that people under 40 years old, so it's only 40 people. And then the one that reading the paper, it's only 4 of those. So 4 over 40. So selecting the one that is sharing common, row and column, under 40 years old reading paper, and then under the total outcome, so under 40 years old. So 40 people, they're under 40 years old. So 4 over 40, 10%. So here's another one. It's quite similar to what we're doing. And this one, you just want to set up that, let's see. So a survey asks people whether the pets are picky eater. For this results, are being a picky eater or being a cat independent or dependent event? Justify your answer. So in order to find out what that is, so the one for the probability that's picky, so that would be 34%. So the reason why it's 34% because that is considered 11 over 25. And then the probability of picky on top of cat, okay, relying on cat here, then that'd be 44%. Okay, so 11 over 17. Well, no. Oh, you know what? This one, once you find out those probability, if they're considered different or if they're not equal, so that means the events are dependent. So the probability of picky, so it's 11 over 50. So 11 over 50, so the percentage would be considered 34%. So let me check that right here real quick. So 11 over 50. No, the probability of picky, so let's see. It's 11 over 25. Right, so 11 over 25, so this one is picky on top of cat, so then that'll be 11 over 25, which is 44%. But if that's just the probability of picky, so probability of picky, then that'll be 11 over 17. That would be 64%. Or would that be 11 over 50? Yeah, this one is one of the interesting ones. Okay, so again, anytime they see something like this, whether that's asking about dependent or independent, so just choose one event. And then you want to find out the column and the rows for the probability. If they don't match, so that means the probability, well, that means the events will be considered dependent. If that would be the same probability, then that would be considered independent event. So it's quite similar to the previous one we did. Okay, so here's another one. So anytime that you find out the probability of cats, okay, so or picky over dog, okay, so then this one would be considered 6 over 25. And then the other one for the probability of picky, okay, so then that'll be considered 17 over 50. Okay, so probability of picky is that 17 over 50. Let's see, would that be 34%? It is. So again, so the rows in the column, if you find out, okay, so 17 over 50, then that would be considered 34%. That would be the probability of picky. Okay. And then the probability of dog overpicking. So the probability of dog overpicking. So then that'll be considered 6 over 17. So you have to do that on the calculator. And that one, it's considered about 30. Wait, it's actually 6 over. The probability of dog. The probability of picky over dog. No, 6 over 25. 6 over 25. So that's why it's what? 24%. Okay, so it's all about the matching here. So 17 over 50. So you want to compare that with 6 over 25. So you find out those two probability if they're not exactly the same. So that means, guess what? They're considered dependent. So going back to this one here, so pretty much the same thing. So the probability of picky, then that'll be considered 17 over 50. Then that'll be 34%. But the probability of picky over cat, so probability of picky over cat, so it's 11 over 25, which is considered 44%. Again, those two percentage, they're not exactly the same. So that's why the event, they're considered dependent. Okay, so this one's quite similar. So now let's talk about something else. So 22, a stone selling school supply advertise a bundle deal. The consumer can pick a backpack, a binder, a pack of pencils, and notebook paper for a set of price. And there are 4 types of backpack, 3 types of binder, 6 types of pencil, and then 2 types of notebook paper. So how many different bundles are possible? So the way to arrange this one, so since we do know that we do have 4 types of backpack, 3 types of binder, 6 types of pencil. So the way to do it is just like 4 times 3 times 6 times 2. So you multiply them all together, eventually it's going to be 144. Because anytime that we need to select a bundle, so that means for the first one, we need to select the backpack. So we do have 4 different types, so 4. And then for the second blank, we do have the binder. We need to select one binder, but we do have 3 different types, so times 3. And then the third blank, we do have 6 type of pencils, so times 6. And then for the fourth blank, we do have 2 types of notebook paper, so multiply by 2. So the way that you want to do it, just multiply those 4 numbers together. So 4 times 3, 12, 12 times 6, 72, and then 72 times 2, 144. And then the next one, they're quite similar, just multiply all those numbers together. So 5 times 5 times 3 times 2. So 5 times 5, 25 times 3, 75, and then 75 times 2, 150. So for 22C is quite similar. And which of the following is an examples of combination? So the difference of combination and permutation. So anytime that you want to choose something from any selections, so if the order does not matter, so then that would be considered combination. So picking 3 books to take with you and on vacations from the selection of 20 books. So let's say that you picked a book randomly. It doesn't matter which order that is. So then that would be considered combination. Again, combination, order does not matter. And which one of the following is the examples of combinations? Selecting the CD, selecting 5 CD to take with you on a trip from a collection of 30 CDs. And then picking 4 sets of towels out of 20 different sets. Again, picking things randomly. Order does not matter. And which one of the example is considered permutation? So the number of ways that 5 people can finish the first through 5th place in a race. So this one, order does matter. So that would be considered permutation. And then another example for permutation, selecting the number of places, the first, second, and the third place winner at the baking competitions. Order does matter. The number of ways 3 people can win 3 different prizes. Again, 3 different prizes. Again, order does matter. Permutation. So here's one of the examples for either combinations or permutation. So a coach company produced 20 cocks a day, so 4 of which are defective, and find the probability of selecting 4 cocks from the 20 produced where none of those are defective. Okay, so we do know that 4 of those are defective, but we need to select the one that are considered none of those are defective. So the way to do it, so we need to set up 2 things here real quick. So let me show you that the formula for combination and permutation. So, okay, let's do this right here. So for the permutation formula, so let's say that we do have n, well, this one's combination, so n choose r. So if that's n choose r, then that'll be considered n factorial over r factorial times the quantity of n minus r factorial. So I'll explain what factorial means. So let's say that n is 5. So 5 factorial, that means like 5 times 4 times 3 times 2 times 1. Then that'll be considered factorial. It's all the way from that, the highest number, back to 1. So 5 times 4 times 3 times 2 times 1, so 20 times 6 times 1, then that'll be 120. Okay, so this one is for the formula of combination. And then the other one, it's called permutation. So permutation is a little bit easier, so that just consider n pick r. So n pick r, that means n factorial over n minus r quantity factorial. Okay, so now let's find out. So back to the problem that we're doing here. So the first thing that you want to find out is the possible outcome. So we need to make sure that none of those are defective. If none of those are defective, then that'll be 16. Okay, so from 20, so because we do have 20 clocks right there, so 20, choose 16, because 16 of those, they're all considered non-defective. And then on top of that, in 16, choose how many? 4. Okay, so that's why we need to use combination. Okay, so again, the question is asking, find the probability of selecting 4 cocks from that 20 produced where none of those are defective. So 20 choose 16, then that'll be the total possible outcome, because we need to force to choose those non-defective cocks. And then 16 choose 4, then that'll be the possible outcome. So 16 choose 4, you try to do that on the calculator or do it separately. So that'll be 16 factorial over 16 minus 4 quantity factorial times 4 factorial. So one thing at a time. So 16 factorial, then that'll be considered 16 times 15 times 14, and then times 13 times 12 factorial. So the reason why that I stop here, because that 16 minus 4, then that'll give you 12 with the factorial, the exclamation mark, that's called factorial, and then times 4 factorial. 4 factorial, just like 4, 3, 2, 1. So what I can do here, I can just cross out that 12 factorial, and then the rest of this, so I can reduce. So 4 times 3, then that's 12, but 4 goes into 16 4 times, 3 and 2, so 3 goes into 15 5 times, and then 2 goes into 14 7 times. So the rest of this is just 4 times 5 times 7 times 13. Again, the 12 factorial got canceled already. So once you multiply the rest of this number straight across, so then you'll get 20 times 7, which is 140, and then 140 times 13. That'll be 1,820. Now this one, it just gives you the numerator. But now we need to find out what that is for the denominator. So 20 choose 16, so 20 factorial over 20 minus 16 factorial, then that'll be 4 factorial, and then times 16 factorial. Again, this one can be written as 20 times 19 times 18 times 17 times 16 factorial over 16 factorial, and then times 4 times 3 times 2 times 1. Again, 16 factorial got canceled. And then 4 goes into 20 5 times. And then 3 goes into 18, which is 6 times. And then we left with the 2 down the bottom here, so nothing can go with the 2 here. So we got 5, 19, 6, 17, and then divided by 2. So 5 times 19 times 6. Oh, you know what? We can reduce 2 by 6. And then times 17, then divided by 2. So we got 4,000, and then 845. If you try to reduce it, so 1820 divided by 4845. Okay, so let's see. So it's better for you to do that on a calculator for this, because otherwise it's going to be very difficult. So eventually, here's what I found. It's 364 over 969. So 364 over 969. So once you divide it, you'll convert that. It's going to be a fraction. It's going to be decimals, and then you need to convert that to a fraction. Okay, so now let's see what else that we have for the rest of this. So this one is quite similar. Okay, so basically it's the same kind of problem here. And now 26. So you're choosing 3 of your 7 trophy and arranging them in a row on the shelf. In how many different ways can you choose and arrange the trophy? So this one looks like 7 pick 3 because the order does matter. So 7 pick 3. Okay, so let's do it right here on the new slide. So 7 pick 3. So 7 factorial over 7 minus 3 factorial. So 7 times 6 times 5 times 4 factorial. The reason why that I stopped there, because 7 minus 3 factorial is just the same as 4 factorial. So we can just cancel them out. So we got 7 times 6 times 5. So 7 times 30, which is 210. So that's one way of doing it. Here's another way you can do it. Because you need to choose 3 trophies. So that means we got 7. So once you pick one of those from those 7, and then we got 6 left. And then choose another one, so we got 5 left. So 7 times 6 times 5, which is 210. So we can do it either way. You can do it with permutation, or you can do it with this. This one is called the counting principle. Okay, so the counting principle for probability. So let's say you don't know what that formula is. You can always do it this way. Okay, so 3 blanks, because you need to choose 3 trophies for the shelf. And then, so start with the first one, so 7. And then once you pick one, so we only got 6 left. And then pick another one, we got 5 left. And now let's see what else. So another permutation. So you're choosing 3 of your A trophies and arranging them in a row. Okay, so same kind of problem. So A pick 3. So eventually it's going to be 336. And then 7 choose 4. 7 pick 4. So 7 factorial over 3 factorial, 840. Okay, so a pizza restaurant allow you to choose any 3 of 8 toppings. And how many different ways are there to choose the topping? So now this one is a little bit different compared to what we did, because the order does not matter. If the order does not matter, so that means we're using combination. So A choose 3. So for number 27, so this one would be considered A choose 3. Again, for combination, it's what? A factorial over 3 factorial times the quantity of A minus 3 factorial. So A times 7 times 6 times 5 factorial, and then 3 times 2 times 1. Again, A minus 3 factorial is the same as 5 factorial, so reduce, cancel. And then 3 times 2, which is 6. So 8 times 7, 56. And that's what we have for the combination. And then the rest of that, again, order does not matter, so that would be considered combination. It's all combinations for the pizza topping that you're choosing here. Okay, so now let's see what else that we got for the rest of this. So basically, that's what we have for this pretest analysis. So make sure that you either fast forward or just rewind to the part that you're not getting through. Okay, so I'll see you guys next time. Okay, so you guys take care.